We live in a base 10 world. Computers operate in a base 2 world. What this means is when we look at numbers, we see numbers like 42, 4 tens, and 2 ones. We understand that 42 means 42. We can comprehend how many items there would be if we had 42 items. A computer, however, uses base 2. So to represent the same value or the same number of items, a computer is going to look at a series of zeros and ones. For example, this represents 42 to a computer. In order to convert from one to the other so that we can understand what the computer is interpreting or how the computer understands numbers, we need to understand where do these numbers come from. Now, I've referred to this number as a base 10 number. Bases define the place value of each digit in a number. So you're probably familiar with ones and tens, as well as hundreds and thousands and so on and so forth. Where do we get those place values from? Well, the reality is in base 10, it's a base of 10 raised to an exponent. So the first place value is always raised to the 0 exponent. Any number raised to a 0 exponent is just 1. 10 raised to the first power, 10 to the 1, is going to be 10. 10 squared is 100, and 10 cubed is 1,000. And so we have our different place values in our base 10 system. 1, tens, hundreds, thousands, so on and so forth. And so what this number 42 means is that I have 4 tens and 2 ones, or 40 plus 2, which equals 42. Now that's fairly straightforward. In binary, the same principle applies. In binary, the base is 2 rather than 10. So each of these different place values has a different number based on 2 to the 0, 2 to the 1, 2 squared, 2 cubed, and so on. So 2 to the 0 is going to be 1. 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. These are the binary place values, or the powers of 2. Each of these digits represents one of these numbers. Now realize we're looking at these numbers in decimal because that's exactly how we comprehend them. We understand everything based on a base 10 understanding of numbers. Computers are still going to look at this as binary digits, but we can understand the quantity that's represented by these numbers by looking at each of the place values as a base 10 place value. So let's look and see, did I actually do this conversion correctly? Is the decimal number 42 represented by 101010 in binary? Okay. So in order to calculate what this value represents, all we're going to do is add up the place values. Now, much like I had 2 in my ones place and 4 in my tens place, or 40, 4 tens, 2, 2 ones, I can do the same thing here. In my ones place, I have a 0, which means I have no ones. Okay. In my twos place, remember this is 2 to the first power, so it's my twos place, I have 1. So I'm going to write down a 2 here. In my fours, again I have a 0, and in my eights, I have a 1, which is 1 8, so I've written down an 8 here. This place is my 16s, and this is my 32. So I have no 16s, I have 132. So I can go ahead and write down a 32. Now if I add all of these up, a 2, an 8, and a 32, you'll notice 2 and 8 is 10, 10 and 2 is 12, and 1 and 3 is 42. Okay? So this is in fact representing, it's the binary representation of the number 42. All right, so let's look at this in a little bit more detail. Now that we understand the decimal place values, the way that we use numbers, we can actually convert between binary and decimal fairly easily. In order to go from binary to decimal, just like I did here, we're going to work through all of the different place values, identifying which ones actually have a value. So let's try another binary number. This one, let's go ahead and do 11001100. Okay? A larger number. First, let's identify the place values. So each of these different digits is occupying a place value, much like my ones, tens, hundreds, thousands. I have my ones, my twos, my fours, my eights, my 16s, 32s, 64s, and 128s. Now remember, I created that list by considering the powers of 2. This is 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, and so on and so forth. And so I get this list of numbers. Now because I have this list of numbers already written out, it's easy for me to remember which base I'm on. I like doing math from largest to smallest. So I have a 128, so I'm going to go ahead and write down 128. This 1 represents 128, much like the decimal 4 here, 4 tens, represents 40. This one here in my 64's place represents the fact that I have 64. Then I don't have any 32s, don't have any 16s, I have an 8, and I have a 4. There's my 8, there's my 4, and I can go ahead and add these all up. So 8 and 4 is 12, plus 8 is 20, plus 4 is 24. 2 plus 2 is 4, plus 6 is 10, and 1 plus 1 is 2. So this represents 204. Okay? Now, can we go backwards? Can we go from a decimal number back to a binary number? Well, and in fact, we can. Okay? So 204, if we have this number and we want to get back to a binary number, we have to consider which place values are we going to need. Think about if we were to write this in decimal. If I was looking at 204 items and I wanted to write it out in decimal, well, I would first begin by saying, well, do I have any hundreds? Here's my hundreds position. I would say, yes, I have 2 hundreds. Okay? And then I might subtract, let's write it over here, 204, subtract 200, and I have 4 left. So then I might look at my tens place. Do I have any tens? And I'm going to say, no, I don't have any tens. Do I have any ones? Yes, I have 4 ones, and so I'll subtract 4 from here. And you'll notice that I've represented that number, 204, in decimal. Now it seems sort of silly to go from decimal to decimal, and in fact it is. It's the same number. But we can apply the same idea to going from decimal to binary. What we need to figure out is what is the largest place value that we can put a number in that will still fit inside of 204. So for example, we know that we at least have a 1. Okay? We know we have 1s. We also have 2s. We also have 4s, 8s, 16. All these numbers are smaller than the number that we're trying to represent in binary. We have 32, 64, 128, 256. Now you'll notice 256, there's no way that I'm going to have a value for the 256 out of 204. So I know that this one's going to be a 0. But I do have 128. And so what I'm going to start doing, move this up here so I have a little bit more room. So in order to represent 204, I'm going to account for 128 items out of my 204 by putting a 1 here. Realize in binary, the only digits that we have at our disposal are a 0 and a 1. Decimal, we have 0 through 9. In binary, we only have a 0 and a 1. Okay, base 2, only 2 digits. 0 and 1 are our 2 digits. So now that we've accounted for 128 by putting a 1 in the 128's place, we can subtract 128 from 204. Borrow from my 2. 7. We're left with 76. So in the 64's place, again, I have 64 items that I can pull out of this 76. So I'm going to go ahead and put down a 1 to account for another 64 items. Now I don't have 32 that I can pull out of 12. So I'm going to go ahead and write a 0, and I don't have 16 that I can pull out of 12. So there's another 0. But I do have an 8, so I'm going to pull another 8 out. Okay, these are all subtraction. I do have a 4 that I can pull out. And you'll notice I'm now at 0, so I don't have any 2s, I don't have any 1s. And if we look at that, we realize we've come up with the exact same number that we started with up here, 11001100. So the process works both directions. Okay? So kind of in summary, if we want to convert from binary to decimal or from any other base, whether this is hexadecimal, octal, etc., if we want to convert from that to decimal, we first need to figure out what place value each of those digits represents. And we'll understand those in decimal because we do the exponents, 2 to the 1, 2 squared, 2 cubed, we evaluate those in decimal. Okay? And so we'll understand what decimal value each of those place values represents, and then we just need to add up the ones that are accounted for. So in this case, 128 plus 64 plus 8 plus 4, those are all ones that we have accounted for. In order to reverse the process going from decimal back to binary, we have to figure out first what the largest place value that we can hold a value in this case 128, which is less than 204, and then work backwards from there, subtracting out what we've accounted for as we do those numbers. Let's go ahead and do one more example. So we're going to start with a decimal number. Let's do a nice big decimal number. So I'm going to do 1010, 1100, 1111. Okay. Now notice that I group my binary digits in sets of 4. There's a reason for that. When we get to hexadecimal, converting between decimal and hexadecimal, hexadecimal is base 16, it's actually very easy to convert between binary and hexadecimal if you have your binary grouped in sets of 4. So you'll often see that. Computer memory also likes to group things in bytes, which is sets of 8, and so you'll have 2 nibbles, which is half a byte, in sets of 4 like this. It's a common way to represent binary is by grouping things into sets of 4. Okay, so anyway, let's get on with converting this from binary to decimal. So first, let's figure out our place values. So I've got my 1s, my 2s, my 4s, my 8s, my 16s, my 32s, my 64s, my 128s, my 256s, I'm running out of room here, 512, 1024, and 2048s. Okay, so big numbers here. So now that I know all of the different place values, these are the decimal values that each of these places holds, let's go ahead and add them all up so that we can figure out what number, what decimal number this represents. Okay, so I have 1 in my 2048s. So I've got 2048 there. I don't have any 1024s. I do have a 512. I don't have any 256s. I do have a 128, and I do have a 64, but no 32s, no 16s. And then I have an 8, a 4, a 2, and a 1. Right, then I'm going to add all those up. So 8 and 2 is 10, plus 8 is 18, plus 4 is 22, plus 8 is 30, plus 4 is 34, 36, 37. Right, 3 and 4 is 7, plus 1 is 8, plus 2 is 10, plus 6 is 16. And 1 plus 5 is 6, plus 1 is 7, and there it is, 2,767. Okay, represented there. So now we've got this number, 2,767. Let's go ahead and go backwards from decimal back to binary. It's a good way to check our work. Okay, so now that we have the decimal version of the number, let's work backwards and see if we can get the binary version out of it. All right, so again, in order to represent this in binary, I need to figure out which place values I'm going to be representing. Now I could cheat and look back at the original number that I started with, since I know what the binary representation should be, but I really want to do this by hand. So I'm going to go ahead and work through all of my binary place values, starting with 1s, 2s, 4s, 8s, 16s, 32s, and what I'm doing is I'm essentially trying to find the largest place value that this number will still fit inside, or the largest place value that will fit in this number. 128s, 256s, 512s, 1024s, 2048s, and those numbers are getting pretty big. And then the next one would be 4096, and I realized there's no way that I'm going to pull a 4096 out of this number, 2,767. Okay, so I have a 0 in my 4096. Now I can work back. Now be careful if you write these out by hand that you don't accidentally skip one of these numbers. Okay? If you do, you're going to end up with a wrong binary number. And what will happen is when you go to account for, let's say, a 512, you'll subtract 512 from here and you'll find out, oh, I still have more than 512 remaining. That can't happen. Okay? If you have more than 512 remaining, realize that all of these added up is actually 511. So even if you had a 1 in every single one of these categories less than 512, each of these place values, you wouldn't be able to account for anything more than 512. So if you have a 1 in your 512s and your difference here is still greater than 512, you probably needed something in your 1024s or one place value higher, whatever that is. Okay, so let's go ahead and see if we can come up with the right number. So first I'm going to put a 1 in my 2048s. And I'm going to go ahead and subtract 2048 from this number. So this 6 becomes a 5, 17 minus 8 is a 9, 1, 719, so no 1024s. Do have a 512, and what I'm comparing here is the base or the place value less than the number that I need to account for, which it is 9 minus 2 is 7. 207. Don't have 256. 256 is greater than 207, so this guy is going to be a 0. I do have a 128. 128. So there's a 1, 9, 17. Again, we have a 9 there. 9 minus 2 is 7, and 0 there. I do have a 64. So again, subtracting 9 minus 4 is 5, and 15. No 32s, no 16s. I do have an 8. Okay, 15 minus 8 is 7, which gives me a 4. 7 minus 4 is 3. I do have a 2 as well. 3 minus 2 is 1, and I do have a 1. Minus 1 is 0. And so 1 0 1 0 1 1 0 0 1 2 3 4, there it is, and that's the original number that we started with. Okay, so now we've gone both directions. Okay, you can practice this on your own, coming up with any decimal number, go into binary, come back, go both ways, and if you come up with the same answer both directions, you're probably correct. If you'd like another way to check it, you can always put it in Google. Google will convert it for you, or if you have a Windows system with Windows 10, the Windows 10 calculator that's built in will do base conversions for you if you switch to programmer mode. Now, I'd strongly encourage you not to use that as a tool. You need to be able to do this by hand. Okay? When we get into some of the topics in computing, such as subnetting and networking, you need to be able to do this kind of in your head or on the fly, converting between decimal and binary numbers. Otherwise, you won't be able to accomplish the tasks that you need to do in a timely manner. So practice this by hand, be able to go between binary and decimal, decimal and binary, using those bases, those place values as your tool to figure out which one represents what number. When converting numbers from decimal to hexadecimal or from hexadecimal into decimal, we need to start by understanding what the place values are in a hexadecimal system. Now, as a reminder, in base 10, all of our bases are powers of 10. So for example, if I have the number 2570, this is my ones place, my tens, my 100s, and my 1000s. We get that by 10 to the 0, 10 to the first, 10 to the second, and 10 cubed. Each of those exponents, 10 to the 0, anything to the 0 power is 1. 10 to the first power is 10, 10 squared is 100, 10 cubed is 1000. Base 10 uses 10 as the base of the exponent. Hexadecimal, or base 16, uses 16 as its base. So if I have 4 place values, for example, I would have 16 to the 0, 16 to the 1, 16 squared, and 16 cubed. 16 to the 0, anything to the 0 power is going to be 1. 16 to the first is 16. 16 squared is 256, and 16 cubed is 4096. Now you'll realize that because this is base 16, I can represent 15 values or 16 values, including 0, in this first digit. So much like in my decimal, if I count from 0 up to 9, I need to go to the next place value in order to get to the next number, which is 10. In hexadecimal, I can count all the way up to 15 in my ones. Well, that presents a problem because I don't know any numbers between 9 and 15 that are represented by a single digit. So in hexadecimal, we add some letters to our character set. So we'll have the numbers 0 through 9, but we will also have the letters A through F. So A will represent decimal 10 in hexadecimal, B will represent 11, C will be 12, D will be 13, E will be 14, and F will represent 15. Right? So each of these letters then can be used in any of these place values to represent that many 1s, 16s, or 256s. Right? So let's see what this looks like. If I have the decimal number 2570 and I want to represent it in hexadecimal, I need to figure out which place value to start in. Now in binary, it was kind of easy because we either had some of a place value or we had 0 of a place value, either 1 or none. In this case, it's a little bit more tricky because we might have anywhere between 0 and 15 of a particular place value. So let's try and convert 2570 into hexadecimal. So we know that we don't have any 4096s. So I'm going to go ahead and put a 0 in my 4096s. But I do have 256s. Okay? Now, I don't just have one, and in binary I would have just put a 1 here and moved on. In hexadecimal, I have more than one 256. So the question is, how many 256s do I have in 2570? Okay? So in order to do that, I'm going to go ahead and divide 2570, can't write. Okay, 2570 divided by 256. All right. Now, because this number 2570 looks an awful lot like 256, it's almost 256 times 10, I can get away with doing this a little bit easier, a little bit of a shorthand, but I might have to count out my 256s off to the side or something like that in order to figure out how far I need to go. Okay, 512, 768, so on and so forth. I know that this is 10, so for the sake of time, I'm going to go ahead and do 10, 2560, which would leave me with a remainder of 10. So I have 10 256s in 2570. So in order to account for 10 256s, I need to put the value of 10 in this digit here. Now realize once again that I don't have 10 as 10. I have to use a single digit. So I'm going to come over here to my letters and notice I can represent 10 with the letter A inside of my 256s. So this is 10 times 256, which is 2,560. That leaves me 10 that I still have to account for. So I don't have any 16s, so I can't pull 16 out of 10. Okay, so I'm going to put a 0 there, and I have 10 ones. Okay, again, I need to put a single digit there that represents 10. I'm going to use my A again. So my hexadecimal representation of 2570 is A0A. And now oftentimes when we're working with hexadecimal, in order to point out that the number is hexadecimal, we write a 0x in front of it. Okay, that's the indicator that what follows is a hexadecimal number. Now it's fairly obvious to see that when there's letters involved, but let's say that I have the hexadecimal number 64. Well, what does that actually represent in decimal? Or is that decimal? Or is it base 8? We don't really know. So we'll often put in a 0x to indicate that this is hexadecimal. Let's figure out what this is in decimal. Okay. So in order to figure that out, we need to figure out what place values these are. This is my 1s and this is my 16s. Again, powers of 16, so 16 to the 0, 16 to the 1. Anything to the 0 power is 1. 16 to the 1 is going to be 16. So I have 4 1s and 6 16s. Okay, so in order to add this up, this essentially is saying 6 times 16 plus 4 times 1. Okay, so 6 times 16, do that real quick in my head, is 96. 96, and 4 times 1 is 4. Okay, we're going to add those two up, and 96 plus 4 is 100. So 64 in hexadecimal is equal to 100 in decimal, and that's why we have to indicate that this is a hexadecimal number, because these are not equivalent. 64 is not equivalent to a decimal 64. It represents a very different value. Okay, let's do a couple of other examples. Let's go something that has 4096. We'll do so starting in 5,000 in decimal, and we'll convert this to hexadecimal first. Okay, so first I'm going to figure out my place values. So I have my 1s, my 16s, my 256s, and my 4096s, and I realize that I'm not going to have anything larger than that because it's fairly close to that. 5,000, the next value up is rather large. As you can imagine, it's essentially 4096 times 16, so 65,536, I believe. So now in order to convert from 5,000 into hexadecimal, so this is decimal, we're going to go into hexadecimal. I made this number intentionally so that we would have 1 4096. So I'm going to go ahead and put a 1 there. 5,000, just get this off to the side so that I can write that. 10 minus 6 is 4. 0, 9, 904. Okay, so then I need to figure out how many 256s do I have in 904. I have at least one, but if I add up 256 multiple times, so 512, 768, 1024. Okay, well now I know 1024 is greater than 904, so this would be times 1, times 2, times 3. So I know that I'm going to have a 3 in my 256s. This is 768. Okay. Borrow from my 9, make that guy a 9. So I have 14 minus 8 is 6, 9 minus 6 is 3, 8 minus 7 is 1. And a good little sanity check is to make sure this number is less than the base that I just came from. If it's greater, then I didn't account for enough here. Okay. So now I have 16 and I have 136. I think I'm going to be pulling 8 out of there. But let's just do it. 32, 48, 64, 80, 96, 112, and 100. This is 8, 128. And I don't think I'm going to have, not going to have another 36. So I have 1, 2, 3, 4, 5, 6, 7, 8. So 16 times 8 is 128. That's going to be my number there. So I'll subtract 128 to 16 minus 8 is 8. All right, and so that leaves me with 8. So there we go. So there was one that didn't have any letters in it at all. So 1,388, or hexadecimal, 1,388 is equal to decimal 5,000. Okay. All right, let's do one with letters just to see what we can do. So let's start with a hexadecimal number. I'll do something nice and easy. So we'll do A, B, C. Okay, so this is hexadecimal number ABC. So hexadecimal ABC, we want to know what does this equal in decimal. So in order to figure this out, we need to figure out what are the place values for each of these different characters. The first one is always going to be 1, then 16, then 256. Again, I'm doing my powers of 16, 16 to the 0, 16 to the 1, 16 squared, 16 cubed, so on and so forth, to get those place values. All right. Now, because I like working from large numbers to small numbers, I'm going to start over here. So the A represents 10 times the place value, 256, okay, which is going to be 2,560. The next one, B, is representing 11. Remember that B represents the decimal number 11. We're going to multiply that by the place value 16. And that's going to be 176, I believe. 10 times 16 is 160, plus another 16 is 176. And then C represents the decimal number 12. The place value is 1, and so I'm just going to have 12 there. Then I can add those all up. 8, 6, and 7 is 13, plus 1 is 14, and that is 7. 2,748 in decimal is equal to the hexadecimal ABC. C. All right, again, great to work with this on your own. Do it by hand. Go from decimal to hexadecimal and then back to decimal. Check your work. You can come up with just about any number and run through this on your own. You can start with hexadecimal. You can start with decimal. Now, if you want to check your work, again, you can use the Google, or you can use the calculator built into Windows 10 in programmer mode, and it will actually show you the correct answers, converting between hexadecimal, decimal, binary, octal. Does a couple of different bases there. And again, I would stress, you need to be able to do this by hand. This needs to be something that you can do on your own. In fact, if you can even do it mentally, that would be great. You can't rely on the tools, because the tools aren't always going to be there. So be able to do these things by hand. Now, I did want to show you one more trick with binary to hexadecimal. So between binary and hexadecimal, normally we would convert to decimal in between. So if we had a number like 1111 in binary, we would go ahead and we would convert that to decimal 15. So this is binary, decimal, and then we would convert that to the hexadecimal. Decimal, I can spell, which would be an F, a single F inside of the ones place, so representing 15 ones. So we could go to decimal and then decimal to hexadecimal using this same tool, but that can be somewhat tedious and take a bit of time. Now, I mentioned when we were talking about binary that there was a trick and why we separate binary into groups of 4. Okay, in order to get to hexadecimal. Now, we've already done this conversion, and if we look back at what that answer was, the decimal representation there, the decimal representation of this binary number is 2,767. Okay. Now, if we were to do the conversion from decimal to hexadecimal, we would find out that the answer is ACF. All right. Going from decimal to hexadecimal, that's what we would figure out. We've got 10 256s, so 2,560. We subtract that out. We've got 12 of the 16s. We'd subtract that out. We'd be left with 15. We'd do F. Now, what you may notice is if we look at each of these groups of 4 individually and convert them to decimal, this one here is if we 1s, 2s, 4s, 8s, looking at them individually, 1s, 2s, 4s, 8s, so it's a 2 and an 8, that's a 10, this is an 8 and a 4, that's a 12, and these guys would be 15. If I convert each of these individually to hexadecimal, from decimal to hexadecimal, this is an A, this is a C, this is an F, and herein lies the trick with hexadecimal. Each set of 4 binary digits can be represented by one hexadecimal character, and the place values actually work out so that if you group these into sets of 4, convert them individually into hexadecimal, you'll end up with the same number. Okay, so that's the trick there. If you're going from binary to hexadecimal or hexadecimal back to binary, you can actually just write this out. So A would be 1010, C would be 1100, and F would be 1111. 10, 12, 15, that's what I'm representing there. And that would generate the same binary number. So kind of neat to represent binary and hexadecimal in that way.